Last week we discussed about the bulk partition coefficients, if you can remember. So we showed an example of calculation of bulk partition coefficients for a hypothetical composition of garnet laserite, right? Why it's hypothetical? Because the mantle composition is variable. So we can just, this is just an example only, right? It's not a measured composition. So that's why it's just a hypothetical composition. This is in the garnet stability field in the mantle. So that means it should be it should be a deeper part of the mantle compared to the spinel and plagioclase bearing zones. Okay, but deeper doesn't mean that it is lower mantle. Okay, still within the upper mantle, but deeper parts of the upper mantle, because the melting is taking place in the upper mantle, and the lower mantle is having more or less primitive composition, primitive mantle composition, something like to something similar to bulk silicate earth composition, right? So you remember the bulk silicate earth composition after the earth's accretion, right? The core separated. The core was formed after maximum 100 million years later, after the accretion. So after 4.46 billion years, like 100 million years, you have to put for core formation from 4.56 billion years time. Okay, and then it the silicate, entire total silicate portion of the earth and the metallic core part were separated. So the metallic core is just the earth's core, but the other silicate portion is called the bulk silicate earth, the entire silicate composition. After that, like 3.7 billion years later, like the bulk silicate earth was also differentiated, forming crust, right? Continental crust. And then the upper mantle, lower mantle separation was also accommodated at the same time. So now we have a differentiated planet, right? Differentiated Earth. So in the upper mantle portion, we have laserite composition. This laserite composition also can be characterized in the context of the depth variation, where different aluminum bearing phases are changing, right? The iron magnesium phases like olivine, pyroxene, they don't change much, but what happens is these aluminous phases characterizes the depth profiles, right? The most shallow region can have plagioclase laserite, and then spinel laserite, and after that garnet laserite. Even garnet can be converted into high pressure varieties afterwards if it's subject to more pressure conditions. So in the experimental petrology, people study about these things, right? For example, garnet conversion to majorite, and pyroxenes, wachlight, like different compositions, right? Those are rare minerals which you can find under extreme pressure conditions, right? It's a polymorph, but mainly converted due to pressure increase when the earth is, I mean, earth's, when the interior pressures are increasing predominantly. Okay. So we discussed about the importance of major elements and trace elements, right? So you can remember the major elements do not show much changes when we consider their geochemical processes, right? But trace elements, they can be strongly partitioned. I mean, at a very minor change, they can reflect a big deflection or something in a trend, right? So here you can see an example of nickel, because olivine gets a lot of nickel with fractionation, with the changing composition of silica composition in the magma or the source region. You can see this type of a variation, right? This type of a variation you can you can see the nickel is changing, right? So increase in nickel composition, according to this diagram, characteristic at a place like here, right? About 55 SiO2 weight percentage, like. That means there should be a lot of uh, olivine crystallization happening. So that's why a lot of nickel is going to the olivine composition, olivine structure, right? So this can be reflected both in crystallization process as well as melting process. If this is relevant to the melting process, then a lot of olivine should have been dissolved, right? Should have been melted, because when partial melting begins, first to melt is pyroxenes, right? Uh, Plagioclase pyroxenes like minerals, and then all of a sudden, sorry, then some little amount of nickel can be incorporated into the melting materials, melting phases. But as soon as olivine starts to melt, a huge amount of nickel will be released. So uh, that's what displayed here. If you take this as the crystallization, because it is not very clearly mentioned in the caption whether this is representing the melt or the residual phases. Okay, so if we consider the solid crystallizing solid composition, then you can take it as when CPX, OPX crystallizing, some little amount of nickel will be incorporated into the system. But as soon as olivine starts to crystallize predominantly, then a lot of nickel will be partitioned into olivine crystal. So if you are measuring the solidified phases or the residual phases composition as a bulk, then you will observe like this. But if you measure the liquid composition, again you will see the same behavior, but that is the opposite. The dissolution of nickel, dissolution of olivine, giving out nickel incorporated in that into the melt. So if you measure the melt composition, the residual melt composition, you will see this type of a variation. Or otherwise, you have to check for the solid during the crystallization. So this is during melting and this is during crystallization. But during crystallization, you have to measure the solid. During melting, you have to measure the residual liquid melt composition. Okay, so these are very important, because that's why we need many samples to analyze also, right? Otherwise, you can't just by analyzing few samples like 5, 10, you can't come up with this type of a trend, because you might see just some variation of spots like this. Okay, you are unable to draw a meaningful curve using this, because you are missing the points relevant to this trend in this region, right? It's not reasonable. So that's why you need quite a large number of samples. At least 30, 50 samples are required in many geochemical work. Okay, otherwise it won't represent the real trends that might be present in the rock, so you can't interpret clearly. So representative samples, selection of representative samples is very important during the field work, and also the sample preparation, right? Carefully you have to prepare the samples, so that you have to avoid cross contamination. You can't have cross contamination. For example, even in this case, if you contaminate this sample and this sample, right? For example, right, during sample preparation, right? Unknowingly, you don't know whether it is contaminated, because sample powders we are dealing with during weighing, because we have to measure very little amount of powder. sometimes like just a few milligrams, 20 milligrams, 10 milligrams, like, right? And if you are using the same spatula without cleaning, there can be cross contamination. So these are very, very important analytical steps that you have to be very careful. Otherwise, uh, these minor contaminations even can cause large variations in trace element trends. So, for example, if simple two cross sample contamination might decrease this composition downwards, and might increase this one upwards, right? But you don't know whether silica was homogeneously contaminated, or nickel was homogeneously contaminated, or both contaminated heterogeneously. So in that case, sometimes you might expect a sample point going up like this, or otherwise some sample point might go drop like that, right? So it depends all on how the contamination was also taking place, right? Therefore, we can't predict these things. So best thing is to avoid this type of contaminations. So geochemical sample preparation is a very important step, and you need a lot of training for that, practical training, skill development to handle the geochemical samples, right? Not only weighing, but after that we have to dissolve the samples in acids and decompose, making a solution, and then you have to evaporate the solution and again dissolve in another acid and again evaporate. So this evaporation process also might cause some cross contaminations, because in fume hoods, right, when you are working under fume hoods, uh, this type of contamination can be taking place in the solid, I mean, in dissolution of samples, right? Some fumes even, right, can cause. So therefore, every step must be very well uh, 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 followed by the given protocols, right? So, and then finally, these elemental separations, you have to do some other chemical wet chemistry methods like column chemistry, or some, there are several techniques anyway, right? Sometimes you might learn some of those under analytical techniques. I don't know whether you have learned it in your third year. Anyway, it's very tiresome also, right? It's very tiresome, but actually once you are trained, it's a fun. Once you are trained, it's a fun. So you can go on doing this for days sometimes. Some people very much interested in doing that for weeks, sometimes continuously. When you get samples like 50 samples, so it's a tedious work, but once you are get used to, that's very nice work, right? And also, once you are get skilled on that aspect, you have a very high demand of for employment as well, because sample analysis in commercial labs it needs a very skillful employees. So so the companies would like to hire you if you are very much competent in this type of geochemical analysis. Advanced labs, international labs in Australia, Canada, UK, many labs. There are many labs. People send samples and get analyzed by commercial means, right? So they have a lot of work. So it's uh, I mean, highly paid also, right? It's very good salary you can get. Okay, so as we discussed the incompatible elements, they try to concentrate in the liquid, right? And once you plot them, their composition, uh, they reflect the proportion of liquid. I mean, how much is fractionated into the liquid phase, or even when you consider about the solid, then how much fractionated into the crystallizing phases, right? So both during melting and crystallization, uh, the the incompatibles tend to partition into the liquid phase anyway. So then you can understand whether there has been a lot of incompatible elements fractionated or not. by looking at the incompatible element composition. So here you can see a compositional diagram showing zirconium uh, composition, but there you don't see uh, a variation what you observed in terms of nickel, right? Probably the same sample set, but like nickel, there is no specific behavior for zirconium. But except for any deviation of trends like these, you have something like some kind of a margin here, right? So in terms of what? In terms of silica composition, right? You can see a break, right, from here and uh, here. That means in this area, right? You don't see much silica there, right? I mean, uh, separation is there from samples, right? So I am not sure why that has happened. Probably some presence and absence of zircon in the bulk rock might have caused this difference, right? Because zircon composition means it's a zirconium silicate, right? So you have a lot of silica in zirconium also. So if no zirconium is there, I mean no zircons are there in a particular set of samples, you will see some kind of a blank composition here, right? Like this. Right. Very acidic samples, you may have got a lot of zircon, so you have high zircon composition, right? High zirconium composition. And then when it comes to intermediate set of samples, again you will have some zircons, but in this particular case, between almost like 62 to 68, like there are no much zircon present. This could be one reason for that, but there may be other reasons also. Without knowing the samples and nature of the rocks, we can't imagine much. I mean, we can't hypothesize many other options. But anyway, it's a kind of a inference you can get from this diagram. Other than that, there is the only implication is that this positive correlation. That means when you have increased silica content, you have increased zirconium content also, right? That is what you call the positive correlation, right? If you have the opposite, then like this, that is negative. Okay, negative correlation. But anyway, zirconium shows a positive correlation with silica. That is the implication, main implication. At the same time, you can say that there is a break in composition due to some reason. One of the reasons could be the one that I explained with regard to zircon, presence and absence of zircon, relative proportions. Some other reasons can also be there, right? So anyway, zirconium is also an incompatible element, so it goes to the liquid phase anyway. Okay, so right now you can consider more details, and also we can compare the trace element behavior with the major element behavior, because you considered previously some diagrams, right? These type of diagrams are called Harker diagrams, right? So that's why it's written here Harker diagram. Okay, so you saw similar Harker diagrams. Normally for Harker diagrams means uh, you have silica. In terms of silica composition, another phase variation is shown, right? But it's not always silica, but you can put magnesium oxide also, right? If you are talking about mafic rocks, then you can put magnesium also there, right? Instead of silica, it doesn't matter. Anyway, those are called Harker diagrams. You had the Harker diagram before. I think you saw in terms of magnesium, aluminium, titanium, many other major element phases also, right? There you didn't see a large variation of major elements because I said they are not sensitive enough for very sensitive. I mean, for minor variations in geochemical processes. But trace elements are very sensitive, so you can trace even not only big or major variation, but also very minor geochemical variations can also be traced. So that's why trace elements are important in geochemistry. So we call the major element in a phase is usually buffered by the system. So that means buffering. Buffered by the system means you don't see any reflection of their change of composition, right? It doesn't reflect much change in composition. That means if you have olivine and iron magnesium can be variable because it is a solid solution, but still it is olivine, right? Even though iron composition is changing, and for example, phosphorite ferrite composition is changing. Here, weight percent of phosphorite is shown, right? But even 20% of phosphorite, and you have another one like 80% of phosphorite, both are olivine, right? Only thing is phosphorite composition is different, right? Even I mean, if for 20 phosphorite composition, we don't put it as a new mineral, right? No, it's still olivine. So that's what we call the buffering. So major elements are buffered by the system itself. Okay, so it varies a little bit only. I mean, phase changes you can't expect. I mean, you can't see olivine converted into a new phase, new mineral, or some other mineral, pyroxene or something, due to this minor change in, not minor, but this change in major element composition, right? So it's a constant phase. I mean, composition is there. It is buffered. It's still olivine, right? So you can see here, you can change the phosphorite phthalate proportion in this diagram. And if you change this variation along this line, or along this zone rather, right? All this zone, if you change the composition, I mean, you exchange iron and magnesium so that uh, in a also you change the temperature as well, right? Along this direction, right? You have to do it experimentally, right? But along that particular direction, that means, for example, if you have 20 phosphorite weight percent and you make it 1300, and you will change the phosphorite composition a little bit weight percent to 40, right? Like this, and you increase the temperature a little bit, still the same, like that. If you go in this direction, there will be no phase change happening, right? So this is the equilibrium uh, composition zone. So you have liquid phase plus olivine, right? Liquid plus olivine. You have both liquid plus olivine, that means solid, and liquid both is there in this region. Okay, in this particular region, you have this both compositions. Okay, right. But if you just arbitrarily change the temperature, for example, starting from 20, you just keep on, without changing the iron magnesium composition, you just increase the temperature of the system. And as soon as it hits the liquidus, what happens? All the solid olivine, because here you have both liquid and uh, solid, liquid and olivine, both. That means liquid and solid is there. So all the solid will be transformed into liquid, because from there onwards, only liquid is stable, right? So now you made a phase change. Now you made a phase change. So as long as you are maintaining your equilibrium conditions like this, right, along this region, you will never get any phase change, right? So that means during the equilibrium behavior, equilibrium region, the composition of the system is really buffer. That means it does not change. So when you change the equilibrium status of the system, this buffering effect will disappear, and you will see a phase change. So that means a real geochemical change you can observe in terms of major elements. Like you observed some nickel variation in trace element here, right? So it's a real change, right? Geochemical change, you observed it. But in the previous case, if you are looking at the major elements, but you are maintaining the temperature and ratios of this iron magnesium along the equilibrium range, equilibrium zone, you will never see any phase change. So during equilibrium conditions, I mean, whenever equilibrium conditions are maintained, mostly in these igneous systems, by terms of major elements, you don't see any phase change or geochemical difference. So that's why we are much concentrated on trace elements, because they reflect irrespective of their equilibrium conditions, right? Because most of the systems that we are looking at are under equilibrium condition. At some places, at some points only, you get this phase transition. For example, during the melting region, when a melt is upcoming to the shallow levels, right? There can be melting happening, right? Further melting happening, mantle upwelling, right? So then you can see real phase changes. But as long as that melt is remained there as a within the Earth's interior, the liquid is mostly maintained with their equilibrium condition. So by looking at the major elements, you can't interpret their geochemical variations. So that's why a lot of magmatology people or volcanic geologists, they prefer studying magma geochemistry to see in terms of trace element variations, not the major element variations. So that's why we need to look into trace elements in magmatic systems. So for the trace elements, it is opposite, means change is drastic. So these changes can be observed in very in a drastic manner, right? So I mean, all of a sudden you can see changes happening. Okay, so you can see here from 35 to 70 almost. From 35 to 70 here, it is shown that so the composition of the melt and olivine does not change, right? You have both olivine and solid in this region. But as soon as you exceed this 70, you will see a phase change, because only solid is available there. So everything will crystallize from there onwards if you change the forsterite composition, right? In previous case, we considered the temperature change, but now you can see how the iron magnesium ratio alone changed. What will happen, right? So the opposite, the other side is also same, right? If you are reducing the forsterite content, everything will be becoming a liquid, right? So that is how it is happening. But as long as they are in the equilibrium conditions, you don't see such variations. Okay, so trace element concentrations. We talked about some laws. Remember Henry's law, right? And Goldsmith's law. Rules, Goldsmith's rules and Henry's law, right? So they behave according to those rules and laws, right? So that means the activity varies in direct, activity has a direct relationship with their concentration. You remember? We talked about the Henry's law, right? Trace element compression is always proportional to its activity, chemical activity, right? Of the system. So if you just take the nickel concentration of the system, we mentioned this when it doubles, when the nickel compression in the system doubles, all the nickel composition in each phases will also become doubled, right? In all phases, right? Irrespective of how much they are in each phases, but it will be doubled. So that happens because it's a rational kind of proportional relationship. Due to this, so for example, right, okay, let's take several phases. Let's take three phases are available in a system, right? So in the magma, so this is the bulk magma. Due to some geochemical reason, so some geological process, the composition doubles, right? Trace element composition doubles. So what should happen for each phases? Every phase also should have its own composition doubled due to that geochemical process, right? So whatever the concentration they had, like for example, one phase might have 1 ppm, the other one has 0.5 ppm, like that, but respectively they will be doubled, right? So therefore, because of this Henry's law behavior of trace elements, it's very important to consider the ratios of trace elements. Okay, the compositional ratios of trace elements, because they similarly change, right? If it is doubled, the other one also doubles. So if you are taking just an individual sample or individual phase, uh, or I mean individual element in a phase, it may have doubled, and you may have another individual element in this phase also may have doubled, but since they all change behavior according to the Henry's law, uh, this doubling happens, but some other some other aspects might influence their doubling behavior also. For example, doubling means you must have you need more and more that particular element to be partitioned into this phase, right? Doubling doesn't mean that it automatically happens. It's some each and every ion or atom should come into this element to this phase to accommodate into their crystallographic sites. That means it has to be partitioned. That is what we call the partitioning, right? So this partitioning behavior can be influenced by other factors, right? Although the trace element should behave according to the Henry's law, uh, this partitioning procedure, which makes doubling or which makes the elements to behave according to the Henry's law, can be affected by other factors. For example, maybe sudden temperature drop, or some another crystallization, or another magma mixing, or some other process can cause this partitioning to block, right? So in that case, in this particular element, in this phase might have not been doubled to 100%, right? It may have doubled to 80% due to some disturbances, right? So you think that it was doubled, but it has not been really doubled, okay? In this case, it may have doubled to 90 or something, right? So it might be not reflecting the really the two phases are doubled in composition, but the effect of this final composition is significant, because this is 80% and this is 90%. But to avoid the influence of this disparity, you can take the proportion of one element, proportion of that particular element concentration in that in one phase to the other one, right? So you take this, suppose this one is A and this one is B. So you take the ratio of the compositions in these two phases. So in that case, mostly this ratio reflects a more reasonable value than you are taking an individual value and go for some interpretations. So that's the reason why in geochemistry people use trace element ratios. Often trace element ratios are superior to the concentration of a single element. So that's what geochemists believe. So therefore, they identify the they identify the ratios of these elemental concentrations in order to identify their individual roles of that particular mineral in a given system, right? So most of the time you may have seen in papers or in reports or books, people have used trace element ratios, right? But remember, you can't take any ratio, right? You can't take any ratio, but you have to consider the two elements which behave similarly also. I think we mentioned that in a previous lecture. The closely aligned two elements in the periodic table can give you similar behaviors, right? Similar geochemical behaviors. For such elements, it's better to have uh, a ratio considered there, right? Because they are supposed to behave similarly, and the more better way of representation is ratio. So therefore, selecting such elements would be ideal for geochemical interpretations. So people use trace element ratios because of that, right? So this is very important because ratios do not oversimplify the nature of geochemical partitioning behaviors of trace elements. So therefore, it's important to take ratios in some cases. Okay. Uh, Sometimes when you take an individual element and try to figure out a geochemical behavior of the system, you might see some kind of strange patterns, right? For example, even the previous example that we saw here, right? This one, right? This silica gap here, right? Might not be the reason that we just a while ago discussed, right? Zircon relationship, right? It may be related to something else. To to confirm it, you can use some trace element ratios and see how they vary, right? So against silica, you can plot the suitable trace element ratio also here, right? So then if that also shows the same behavior, then you can be confirmed on that, right? So like that, several trace element ratios you can try and see uh, how they are going to change, right? For example, if you are thinking of zircon effect here, instead of zirconium here, you can take zirconium over hafnium, right? Zirconium over hafnium, because hafnium is also partitioned into zirconium, as into zircon, and also they are similarly behaving. So you better look into this behavior. So in that case, it should be consistent, right? But when you take hafnium, if this gap disappears, then you have to rule out this is not zircon matter, right? So likewise, we have to take several cases, and then only we can come into a conclusion. So that's why when we are writing a paper or developing a manuscript, you have to try a lot of interpretations using your obtained results, right? Anyway, what you have is your results only, right? ICP-MS or uh, XRF or whatever the trace element compositions, that is what you have in your hands as results. So you have to interpolate, you have to manipulate all these results in terms of different factors or different parameters, and then you discuss their each merits and demerits, right? That is what you are doing in your discussion part in your paper, right? And then you come into conclusions. So this is how you develop your research paper, okay? So for that, you need actually the basics, the understanding. So that's why you are supposed to learn the principles of this geochemistry and advanced concepts in petrology, in magma This is very important. So therefore, these are incorporated into your syllabus in advanced igneous petrology, right? So these will be very important when you are doing higher degrees, right? If you go to a company or industrial oriented job, unless you are going for a modeling firm or geochemical interpretation or sample analytical company, you might not use all these advanced concepts, but still will be useful for your industrial work. But if you are really going to analytical place, industrial place, where you have a lot of analysis to do and interpretations and reports, then this knowledge is very, very important, right? So if you are doing a PhD, definitely you have to learn more and more uh, in terms of dynamic systems, right? We are just considering very static systems, right? But some magnetic systems in the nature, actually they are very dynamic. That means every second some new magma batch is inputting, I mean mixing with that. So the composition varies dynamically. So you can't simply interpret all this type of behaviors like what you are applying to some static systems, right? So it's very difficult task. So that's why we need some softwares also to do petrological modeling. Okay, there are some softwares called IGPET, uh, Magma. Several softwares are there, so you have to use them also, right? Okay. Okay, do you have any questions up to this content? Okay, so some implications you can take from uh, from the ratios, as I said, and also uh, you can just consider the partition coefficients as well when you select uh, two elements for a ratio consideration. Okay. So, in terms of yeah, potassium is sometimes taken as a major element also, right? It depends on the rock, how much potassium is there. Right? If it is in large quantities, you can take it as a major element, right? Like amphibole bearing rocks, a lot of, and mica bearing rocks, there are a lot of potassium, right? It may be in weight percentages than in ppm, right? Anyway, the point is potassium and rubidium behave very similarly. So no problem. You can take these two as a ratio. So you can take potassium to rubidium. So it is supposed to be almost constant because the change of potassium should be equal to change of rubidium in magnetic systems. So therefore, most of the cases, K to RB ratio, irrespective of their compositions, should be almost constant. Okay, so that is another plus point. So in amphibole, almost all the potassium and rubidium resides on it. I mean, unless you have mica in the rock, all the potassium will be there in the in amphibole. So you can see the partition coefficient for amphibole here. Rubidium is 29. Potassium is very much higher than that. It is not shown here. Uh, so that indicates a lot of potassium and rubidium can partition into amphibole. Okay, right. So strontium, if you take the strontium is, oh, these are alkaline elements, right? Potassium, rubidium is also even alkaline elements. So you can take strontium, barium also, right? They are also behaving similarly. So the reason, okay, just a minute. Yeah. Uh, for example, feldspar, if you take plagioclase feldspar, lot of strontium uh, is going into plagioclase. So that means it is excluded from most common minerals, other minerals. It's going away from other minerals and concentrated into plagioclase, right? So if you take alkali feldspar, there can be a lot of barium coming into that compared to plagioclase, right? Barium. So barium likes much alkali feldspars than plagioclase, but it doesn't mean that barium does not go to plagioclase, right? So anyway, strontium and barium is also okay for feldspar if you are taking feldspars. So here you see 1.8, the partition coefficient, and barium is 0.23, right? Still okay, right? It's not like 0, 1 or something. If it is like that, then they have no preference, right? If you get some partition coefficient like this, 0, 1, right? For example, nickel, 0, 1 partition coefficient for plagioclase. That means the nickel does not like plagioclase anyway, right? For olivine, it's 14. That is a comparison anyway, right? So if you are considering feldspar bearing rocks, right, like granites, then you can consider strontium and barium as a uh, two minerals, two elements that you can consider for ratios. And compatible elements, if you are taking compatible elements, nickel is best for olivine bearing systems, right? And also chromium and scandium, right? Uh, in pyroxenes and also olivines can be taken into consideration. So you can, if you compare pyroxene and olivine in terms of scandium and chromium, right? Pyroxene has much higher preference for chromium, I think. Yeah, you see here the partition coefficients. If you see CPX, OPX, partition coefficient for chromium is 10 and 34, right? But for olivine, it's 0.7. 0.7 is also high, but this is 10 and 34, right? So that effect you can distinguish olivine and pyroxene uh, uh, determining geochemical changes in melts, right? So if you want to find out whether olivine dominated or pyroxene dominated magmatic system, then you can go for these ratios, right? Because chromium likes much pyroxene, nickel likes much olivine. So according to the change of this ratio, whether it is being high or low, you can think of what is dominant there, right? Similarly, you can use the scandium also, right? So especially with the fractional crystallization, because during crystallization, these elements go into the respective solids, right? Respective minerals. For example, if you see a drastic drop in nickel in fractional crystallized material, I mean the residual system, if you see a drastic drop, that means from the system, some mineral has crystallized, which attracts a lot of nickel, right? So that means it should be olivine, right? So in the system, you get a drastic drop of nickel. Uh, so once nickel is gone, chromium goes, uh, I mean, chromium concentration automatically increases, right? It's like from a class, girls and boys are there. Several girls went out, then boys concentration in the class will increase, right? The same thing. You can imagine like that, right? So this type of geochemical interpretations, you have to carefully select uh, the elements, right? So you can look at the partition coefficients table and select similar, I mean, better elements. But you don't take very drastic change elements, like for example this is 14, and if you take 01, right? For example, in plagioclase, if you want to see the nickel effect, uh, I think it's not suitable to take this I mean, in a plagioclase bearing melt, if you want to see the olivine effect, it's not a good idea to see this select nickel. You have to take something else, because for plagioclase, nickel has a very little partition coefficient, right? So you don't get anything reflected there. It's very low, right? It's very low. So therefore, for a mafic system, you can take nickel, right, and olivine. But for a felsic system, you can take some other elements, because in a felsic system, you don't expect a lot of olivine also, right? So therefore, pyroxene like phases will be the dominant there, in addition to felsic phases. So you better take something like chromium instead of nickel. Okay. So here you have um, another table, a portion of a table. There you have basaltic and andesitic rocks. Previous table you had, yeah, the same basaltic and andesitic. And these elements are given, right? So you can just compare, because in basaltic and andesitic systems, definitely you have all these type of phases, right? Even olivine can be there because it is basaltic, means mafic system, right? So in such a system, you can take whatever the elements that are shown here, because they may show you some kind of significant effects. So you can take ratios uh, like this: rubidium strontium, or strontium barium, or barium nickel, or nickel chromium, right? These ratios you can take. Nickel chromium already we have taken, see, like that. Okay, right. So any questions? Do you have any questions? This you have to go through again on the same concepts, because I mean, before the exam, you can refer the textbooks in the library. We have several igneous petrology textbooks, and also there is geochemistry textbooks. At least you have to see uh, the textbook called Using Geochemical Data. The name of the book is Using Geochemical Data, written by Hugh Rawlinson, right? You just type the Rawlinson there in the search computer in the library, and you will get that. Okay, it has examples, very nice examples, simple examples about these concepts, these geochemistry principles. Okay, so that's a very important book. And also online, you can search for W.M. White, geochemistry book by W.M. White. Uh, Chapter wise PDF, you can find copies, right? Full book can be found, but chapter wise, right? Freely available. So you can download that relevant chapter and also go through the content. That is also in very good book. And I also have taken some examples from there. Uh, so it's very interesting book. That's available. You just make a Google search, W.M. White Geochemistry. That book is available in PDF forms, chapter wise. Okay, right. Now we will have to move to a new section. Uh, based on our knowledge, previous knowledge, we may have to apply that knowledge in some places. Okay, so you have to consider our previous what we have discussed so far also, right? So now let's see the models of magma evolution. That means magma is generated as a result of partial melting of the mantle, right? Mainly, or otherwise partial melting of crustal rocks, right? So so the mantle melting contributes to continental crust formation also, but later on, continental crust itself can generate some magma, right? So anyway, there are several more models to explain these behaviors of this magma evolution, because once the magma is formed, uh, the nature of its accumulation and percolation has different aspects, and also the origins of these magmas are also different in some cases, right? So there are several models. One model is batch melting, right? So in this case, we consider the melt is formed as a batch, right? So all the formed batch, right? So you have source, and some magma is produced, and this batch as a batch, right? So you have a batch of magma produced from the source, and it remains in contact with the source for some time, right? So it doesn't release as soon as it's formed, right? So with some time after it has reached some equilibrium condition with the solid, some exchanges can take place, right? Elemental exchanges can take place, and then only it moves as a batch, percolates upward. Okay, because the melt is always less buoyant than the solid, so therefore it can go up naturally. So this is called an equilibrium melting also, because the formed melt remains in contact with the solid under equilibrium conditions, right? So, but anyway, variable amounts of melting can take place, right? That is what we call the degree of melting: 1%, 2%, 5%, 10%. At most, maybe 30%, 30 to 40%, right? Not more than that. Even above 30% is not very easy. So anyway, that is the kind of upper limit, right? So this is batch melting. So there are some equations generated experimentally to calculate the concentrations of some elements, right? For example, trace element concentration in the liquid, because you have two phases, right? You have magma and solid, the residual solid. You have two phases there. So the distribution of an element in between these two phases can be variable. So its proportion is given in terms of the partition coefficient and the degree of melting, the fraction of melting, right? So the Cl means trace element concentration in the liquid. So how much the trace elements are concentrated in the liquid here, that is Cl, and how much that particular element is concentrated in the residual solid is given, not the residual solid, sorry, it's original solid. That's why it's given as O, CO, right? Before melting, original source here. We have the source, and then it is subjected to melting, right? Now some elements fractionated into the melt, right? And some elements remain in the residual solid. But for the equation, we take the original source, right? So this is the equation, and this is actually the weight fraction of the produced melt. That is the amount of melt produced, or degree of melting we call sometimes. You can take it as melt volume divided by the whole system volume, melt plus rock. Okay. D is the partition coefficient or the equilibrium constant or the distribution coefficient, right? Which is same as partition coefficient for dilute solutions. Remember the dilute solutions we take directly concentration difference rather than going for activities, right? Simplified versions, but in if you are doing a PhD like thing, you can't go simply into these concentration ratios, right? You have to take into activity concentrations also, activities and concentrations together, right? Uh, but this is simplified. Uh, assuming the liquid or the melt is diluted now, right? It's not very concentrated, it's diluted. Magma means a diluted composition, right? Compared to its source. Its source contains a lot of trace elements, but in the magma you have little compared to that because it is partially molten. It's not the complete melting also. That's why. So here you have a D given for a given element I, right? Its composition in the solid and its composition in the liquid. So you can remember the definition, right? We always take the solid at the numerator. Okay. So batch melting is here. So if we take this ratio, that means concentration of an element in the liquid divided by concentration of the element in the solid. Here, this factor, this parameter. If you take this one and you plot it in using F, the degree of melting, right? This one, F, right? So this equation will be represented in that diagram. Actually, the graph of this equation is this one. Right, so for various values of D, because D also matters, right? D also matters. D means the concentration of that element in the solid divided by concentration of that element in the liquid, right? So that also matters. So depending on that composition, if it is D equals 1, that means if both are equal, right? If both are equal, solid means its original source. Okay, always we take the original source. So if it is equal concentration, it is just should be 1, isn't it? If it is equal, right? So if it is equal, I mean, it's not a natural situation anyway. Right? So you can see here, if D less than 1, if D is less than 1, so that means if D is less than 1 means here, a very high concentration in the melt. So you should see the elemental concentration in the melt. That means this factor should be going very high, right? So you see, even at a very tiny degree of melting, very little degree of melting, something like 0.05 or something, right? You see 10 times higher concentration is given compared to its original composition. Original composition is here. See 0, it's 10. 10 means 10 times higher than its original. So that means at very low degree of melting, a large amount of trace elements are fractionated into the liquid. So especially for low degree of melting. So this is low degree of melting because when it goes to higher degree of melting, you can see only very little amount of elements go into the melt, right? Very little here. This is very little, but in these type of cases, it's very large, 10 times, even more than that, 10,000 times sometimes. But it all depends on the amount of liquid. So here it's D equals 0, 0, 1. So in that case, it's almost infinity, right? Very large amount. So incompatible elements will show very large elements, elemental partitioning into the liquid in such cases. Okay. So this is important. The behavior of this one is also important. How its composition changes. So if you see the caption here, caption to this figure, variation in the relative concentration of a trace element in a liquid versus source rock as a function of d, the fraction melted, right? D means the fraction melted, and the variation of trace element in a liquid versus source rock is shown here by this ratio, right? Using equation 9.5 means that the previous equations that we considered here, this one, this equation, right? For equilibrium batch melting. So this is what you call the batch melting equation. So this equation is called the batch melting equation. So you can see how they behave, right? For a very little degree of melting, a large amount of incompatible elements are fractionated. So this is a very important feature of batch melting. So you take the highly incompatible element here, highly incompatible elements. So greatly concentrated in the initial small fraction of melt. So that is what we just looked at. Very little degree of melting means the very initial melts, right? So at very initial melts, a large number of trace elements, I mean amount of trace elements are gone there, right? It's highly concentrated. The initial small fraction of melt. So when you increase it little bit more, 0.1, it drops a little bit. Again, if you continue, drops further here, right? And if you continue further, it drops further and further. All right. And finally, it's very diluted, right? It's very, very diluted when you increase the degree of melting, right? For example, when it goes to 2, 4, 10 even, right? 10 is almost 0, right? 0.1, very little. Okay. So at the very beginning of this melts produced, in match melting, you can expect a large concentration of incompatible elements in the initial drops of gas. But with the continuation of its melting process, partial melting, because you know the partial melting can continue for millions of years, right? So at the early millions of years, I mean at the very early stages, uh, you can see a large amount of trace elements are scraped off from the liquid, from the magma. Sorry, from the source to the magma, produced melt. Okay, so early produced melt, early formed magma contains a large amount of incompatible elements in a batch melting scenario. So gradually, it will be diluted. It will be less concentrated. But it doesn't mean all the incompatible elements contained in the solid will go into the liquid. No, it's not like that, right? It gradually dilutes and retains some incompatible elements in the in the source as well as a residual solid. That also happens. Okay. And if you take much higher concentrations, we already discussed, uh, much higher concentrations means, in other words, we'll discuss it in another way, compatible elements, right? These greater than 1 means the element is no longer incompatible, right? It prefers the solid phase. So that's why you don't see many of incompatibles coming after D is greater than 1, right? If your this D value is greater than 1, then you don't see a lot of incompatibles coming. So that is obvious, right? That is normal, natural, right? From here onwards, so its implication is from here onwards, you get mostly compatible elements into the solid, whereas before less than 1, you get most of the incompatibles into the melt. So that is why the incompatibles are getting diluted in the liquid due to the reason of more incompatibles are coming into the liquid, right? It's like for a class, if you get more and more boys there, so girls' concentration gets diluted. That's it. If somebody is entering into the class newly, the overall composition will be drastically changing if the number of entrants is very high, right? So that is what's happening there, right? So if you just want to measure the compatible elements, then their composition will be large, but we are measuring here the liquid incompatible elements as given in this graph as a draft concentration profile. So you will see gradually incompatible element concentrations are getting down, right? But on the other way, if you want to follow up the compatible elements will be gradually getting higher and higher in concentration with the gradual melting, right? So for low degree of melting, here you see very little amount of incompatible elements as we mentioned before. But if you draw the real graph for the compatible elements, that means for the compatibles, just only for the compatibles, you will see they will get concentrated heavily uh, for high degree of melting. So these two processes are opposite. Here we are looking at the trace element composition in incompatible composition in a liquid. That's why you see it's a gradual drop, concentration drop. Okay, so if the F is reaching 1, F is reaching 1 means what? The amount of melting, right, is almost 1, right? F here. If this is 1, if this ratio is 1, right? So that means melt to melt plus rock, that means source ratio is 1. Then what happens? As F goes to 1, what you can think of uh, this equation, in terms of this equation, everything you can replace to 1 there, right? So if you take 1 here, 1 minus 1 is 0. So this d1 component entirely goes out, and F becomes 1. So Cl over CO will reach to 1, right? 1 divided by 1 equals 1. So Cl over CO becomes 1. So that means compression in the liquid will be equal, almost equal to compression in the solid. So this might show you a complete melting stage. A complete melting stage. That means everything which was available in the source has gone into the liquid, right? The total melting has gone to and contributed to the melt, but it never happens in the nature. Usually this, I said the degree of melting stops from here, okay, under natural systems, because you need a huge amount of heat if you want to increase the melting from the onwards, right? Naturally, it's not happen, and that heat is not supplied naturally unless in very rare situations where you might have a plume, mantle plume, okay? So such mantle flume can provide additional heating so that it can go up to a large amount of melting, right? I don't know whether it can reach is still one, but anyway, it can go up to higher amounts. Okay, right. So that's why during the supercontinent formation, when these plumes hit, a lot of magmatic systems make everything melted. So I mean, more very strange partial melting situations happen. Okay, so if you have uh, no melting at all, like I mean zero, if it is zero, then you can reduce this equation to what? F0. You put 0 here, so it's 1, then 1 over d becomes 1 over d, right? It becomes 1 over d, right? So if it's very little amount of melting, if you are given in a problem that very tiny amount of melting, then you can assume your CL over CO is almost equal to 1 over D, right? That is possible given that the system has not contributed enough amount of melting. Okay, so if you know the CL of magma derived by a very small degree of batch melting, and if D is known, that is distribution coefficient is known, you can just directly estimate the concentration of that element in the source region, right? So if you assume that, that's why most of the problems we assume sometimes very little degree of melting has taken place. Of course, it depends on the petrological observations. And then you can, by using the melt component, which is available now, because it's a basalt, for example, right? You collect the basalt rock and you measure and you assume that very little degree of melting has taken place, because if you see not many melt patches or melting features melt ribs or some melt inclusions in thin section, right? So you can assume only a little amount of melting has taken place. So in that case, you can just assume that very little melting is there. So therefore, you can directly uh, make your ratio equal to 1 over D, right? So because D is known, it's experimentally determined. You have tables given, and you can replace it there, and you can measure the basalt composition, the particular elemental composition in the collected basalt. This one is unknown because we don't know the source region composition in the mid-ocean ridge, right? So you know this one and this one. So therefore, you can directly estimate this one or source composition, right? So that is possible. So such kind of things can also be uh, carried out successfully in some situations, right? But of course, we have to do some assumptions because we don't know really what happens during mating. But of course, once you have some evidence in thin section, that is a real record of the rock, so you can make some reasonable assumptions, right? So that it will give you the source composition, right? So that's how the Earth's composition also determined, right? Source composition. Otherwise, how do you know about bulk silicate Earth composition? There is a paper in chemical geology, uh, that is McDonald and Son, right? Who determined the composition of the Earth, right? So there are a lot of assumptions there, of course, but those assumptions are based on uh, observations made on thousands of samples collected in mid-ocean ridges, Hawaii, plume hit areas, crustal materials, everything, right? Considering a huge database of samples, you can come into some assumptions and do some calculations. That's how the composition of the Earth is determined. So you can search that paper also. It's available freely in PDF form. You can type the composition of the Earth. Just type composition of the earth, McDonald and Son. McDonald, McDonald and Son. Right? They made a previous contribution also that is called Son and McDonald, 1989, that one. But it had some errors and it was corrected in the second paper, McDonald and Son, 1995. So that's a very important paper that you have to use in some of your diagrams also. Normalization. So we will come to the normalization of trace elements later on. Some additional process that we have to do before getting them plotted in some diagrams. So then you will see these references are cited there. Okay. Right. Any question? Okay. So similarly for incompatible elements, you see uh, what happens for incompatible elements. Like, for if when you have F0, that means I mean almost no melting. So it's almost the source composition, right? So here almost the entire melting, right? It reduces to 1, right? So in this case, you can take some incompatible elements. For example, uh, if you take incompatible elements in a solid, right? So if it is not melted very much, right? So you can take uh, this this ratio almost 0, right? Because if it is an incompatible element, if the f is 0, if f is almost 0, if we are assuming f is almost 0, that means there is no much melting is taken place. So almost all the incompatibles should be there in the liquid if the melt is present. So here uh, this is a huge amount. I mean, the denominator is large, so numerator is small. Therefore, it can the entire ratio will go to almost 0, right? It's like 1 over something like no, sorry, yeah, 1 over say 10 to the power 9 or 10 to the power 10, say, right? So this ratio becomes very, very little, right? It's something like that, right? So you can just imagine like that and make this ratio to 1 over f, right? Like we did in the previous case, right? 1 over f, it will reduces to 1 over f for incompatible elements, remember, for incompatible elements. So if we know the concentration of very incompatible element in both magma and the source rock, that means if we know the incompatible element ratio in the present magma and also if we know the source composition also, right? Because source composition can be determined uh, by some other process. For example, you can find a lot of source compositions in McDonald and Son paper, right? It describes about Earth's composition. So mid-ocean ridge basalt composition, lower crust, upper crust, all these sources. These are the sources for melts, subsequent melts, right? So we can get the composition. So once we know these two, you can find out the fraction of melting of that particular rock. That means how much it contributed to melting. I mean, how much? I mean, it's 1% or 2%, 3%, or what kind of a percentage it has contributed during the melting of the source. We can determine because F is unknown, right? Once you collect a rock, you don't know how much the degree of melting there, right? So you can determine the fraction of partial melt produce, amount of the melting. Right? So these type of tiny things are possible to do when you consider this type of examples, right? By getting this batch melting equation, as long as batch melting is considered. There are some other models of melting which we haven't considered. So we can go through those melting also, right, at the next stage. Right, once we finish this batch melting, we can go to that thing also, right? Okay, so we have one example for rubidium and strontium. I don't know whether you are given the all concentration. Okay, let's see here. Yeah. So first, we need the weight percentages, right? Mineral modes are given, density is given, and weight proportion you have to do. I mean, you have to consider it into weight proportion and then weight percentage, because weight percentage, if you are not given, and if you are given only the mineral modes and densities, then you have to go to the weight percentage. I mean, you have to convert it into weight proportions, right? So because density is the mass divided by volume, right? So the mineral mode means it's a volume, right? It's because it's given 15% or 30% or 50% or whatever as a model percentage, right? So it's a volume percentage of mineral actually in a 3D rock. So we have to convert the weight percentages, and then these weight percentages you have to use to calculate the bulk partition coefficient, right? Bulk partition coefficient, because you are given the individual partition coefficients for elements and minerals, because you have a table, right? A table of t values. So the bulk distribution coefficient is calculated using that. Right? For in this case, we are considering rubidium and strontium, right? So because this is a whole rock, represented, right? Whole rock represented. This is a basalt, okay? Basalt. Instead of giving you the weight percentage of this basalt analysis, you are given mineral percentages, mineral model percentages and densities, and from that you have to calculate the weight percentage. If you are given directly the weight percentage, no problem, it's easy. Like in the previous examples we did for the bulk distribution coefficient calculation, you can directly do this bulk distribution calculation. But here you are given the model percentages, and then because once I mean if the XRF data is not available, you can go for the thin section, right? You can just investigate your thin section and find out the model percentages and get the corresponding weight percentages, right? This is remember, this is an approximate calculation only, right? This is not a very precise calculation, but for some situations this is enough for our weight percentages determinations. But if you need it very precisely, then you have to go for XRF, right? For geochemical interpretations, you have to go for XRF anyway. But if XRF is not available, you can count all the minerals which has these, I mean, possible partitioning of rubidium and strontium, for example, olivine, OPX, plagioclase, all the minerals which is available in your rock, given rock. If it is pyrrhotite, you have to take all the mineral modes there, right? But these are the major minerals they have taken here for this particular problem, because these are the major elements that you can find, major minerals that you can find in a basalt, right? Others are some tiny amounts of minerals. So you have to convert them into weight percentages, because once you calculate the mass, you can convert it to weight, and here you have the weight proportion, and you have the total here, right? And from this total you can calculate the percentage, right? How much percentage? 54 out of 303 into 100, right? So like that you can calculate the entire percentage, and then you can go for the bulk distribution coefficient calculation. And then we can use the batch melting equation. We can use the batch melting equation, which was given before here. And we have the bulk distribution coefficient calculated. And we don't know the composition of rubidium and strontium in the liquid and the source. We don't know. In the also the fraction of melting is also not known. So what we do is we have two unknowns in this equation here. Now this one is unknown and this one is unknown, right? Only thing is this one is known. So what we do is we take the entire ratio here for variable amounts of D's and F's, right? Here you take variable amounts of F because F is unknown. So you can, F can be, what are the two possibilities for F, right? I mean the maximum values, the N values for X. It can be F, it can be 0 or 1, right? All the other values should be in between these two, right? So therefore, you take everything. You take all the range. You take all the range because we don't know which one corresponds to this situation, right? So you take all possible F values, right? Starting from 0 to 1. And then you have D, you have calculated D for rubidium and you have calculated for strontium, right? So you apply that value, and for each element you find the ratio of Cl over Co, right? You apply for rubidium, for example, you have the D value calculated and you apply that there, and you apply from 0 to 1 all the possible values so that you will get some numbers here for rubidium composition in the liquid. This is the possible rubidium composition in the liquid for different F values, right? If the F is 0.1, then rubidium should be this one, right? So likewise, all possible values for rubidium is calculated, and similarly for all possible strontium is calculated here, right? So uh, this will give you all possibilities for all melting degrees. And if you want, you can have the rubidium strontium ratio as well, right? So it is given here, that you just divide each other to get the ratio, right? Now this is one approach actually. Once you don't know the uh, the real some of the real parameters, right? So you can make actually later an XY graph also, right? If you want, you can make an XY graph also to plot them and to see how its variation, right? So various, I mean, all possibilities of the melt that is arisen from this particular composition is represented in that table, in the previous table, right? If very little degree of melting, what happens to the strontium and rubidium? If it's a very high degree of melting, then what happens to the rubidium and strontium, like that. So you can see at very low degree of melting, rubidium is there 9.35. When it comes to high degree of melting, rubidium is 1 point something, right? So you can see the rubidium variation, rubidium composition is decreasing with the degree of melting, right? Rubidium composition is decreasing with the degree of melting. So if this is degree of melting, and this is the rubidium composition that we just calculated, you can see it's decreasing. So what does it mean? Rubidium is a compatible element, right? Sorry, incompatible element. Rubidium is definitely, it confirms that rubidium is an incompatible element, because you see, previously we discussed about this, right? Whenever incompatible elements are there at a very little degree of melting, the incompatibles will be high in concentration, right? When it goes to higher degree of melting, the incompatibles will drop, right? So the similar behavior is observed here for rubidium. But if you take the strontium composition there, what is characteristic there? Strontium 1 point something, 1 point, 1 point, 1 point, 1 point, like that. There is no drastic changes like in rubidium, right? So it means for strontium, the system behaves almost constant like, right? Like this, not very much changing, right? Not very much changing compared to rubidium. So these are two different aspects of uh, aspects of trace element behaviors. Okay, so if you take the ratio here, if you take the ratio of rubidium and strontium, you can clearly see that is dropping, because rubidium is dropping, so ratio should also be dropping. But this strontium behavior is almost constant, right? Strontium behavior is almost constant, so that doesn't affect much on rubidium's behavior, right? Because it is like you are dividing its composition by one. It's something like that. So that's why rubidium and strontium uh, can use to filter out some problems related with third factors when you take just rubidium composition, because rubidium is an alkaline element, so it can be affected by other processes as well. For example, if some fluid phases are available when the magma is coming up, right? If it is a subduction zone, for example, think, right? If this magma is coming up to the subduction zone, so in the subduction zone there are so many liquids available, I mean fluids available, aqueous fluids, water, because sediments are there, some seawater circulations can be there, hydrous mirrors are there, right? So they can affect largely, because rubidium likes to partition into fluid phases, especially aqueous fluids. So in that case, if you are just taking rubidium concentration only for geochemical interpretations, so rubidium composition might have affected secondary processes, later processes, right? But strontium is not like that. It's more or less constant in this type of behavior. So if you take the strontium composition also, uh, then it should be identical behavior. So if rubidium decreases, rubidium strontium also should decrease, right? So both these parameters can be compared. Rubidium composition and rubidium strontium composition can also be compared together in parallel. So if you are looking at these two ratios and observe something like strange behavior, for example, rubidium decreases, but rubidium strontium ratio increases, or something like that, with increasing degree of melting, then you know that some special process, I mean, some disturbance might have happened to the system, right? Otherwise, you should expect the same type of behavior, right? Similar type of behavior should be expected. Right? But if some other process has affected, then you will get it reflected from rubidium strontium ratio also. But if just rubidium strontium rubidium's ratio, or sorry, the rubidium composition also, I mean, if you are just concentrating on the rubidium's concentration, then you will see some changes, but these changes might not reflect what, I mean, you can't trace these changes according to just only rubidium concentration, because some fluid may have taken out some rubidium, and sometimes it might have given into, I mean, it has input some rubidium concentrations, but they are only reflected in this region, which is not easily recognizable just by rubidium composition. You might only think that, okay, rubidium should decrease. So anyway, it has decreased, right? It is decreasing. So no other process has affected. But if you take the strontium also, because strontium does not get affected by this type of other processes, then uh, you will not see just decreasing, but you will definitely see some disturbance to the ratio, right? Which should not be disturbed. I mean, it should be smooth unless some other secondary effect is there, right? So if you get still some disturbances in the ratio, then you are confirmed that this must have been a real secondary process. Secondary means a later process after melting. Primary process is the melting. Secondary process is maybe fluid interaction or melt interaction or some mixing or something like that. Okay, so like that we can compare using our given compositions, even if we don't have real measured XRF measured compositions also. Okay, so we can plot the one that I explained here. This table can be plotted and see real change. Actually, it's not linear change as I said before. I just simplified it. But if you plot it, you will see the same type of a behavior that you observed here, right? It's a curve, right? It's a curve. It must be a curve. That is the typical behavior. So you get rubidium as a curved behavior, but strontium almost linear behavior. So here you see strontium is going to have a linear behavior, but rubidium is giving you a curved behavior like this, right? So this is how they change for different degrees of melting, and this is what we call the progressive batch melting, right? Progressive batch melting. So this is why we call it progressive batch melting, because from 0 to 1, it doesn't need to be from 0 to 1, but from lower degree to higher degree, right? Because above 40% melting is very difficult, right? So even from here to here, you can take it as progressive melting. So in a progressive melting, highly incompatible elements like rubidium can be behaving like this, whereas strontium-like elements can behave like that. But it is given for a basaltic system. Like remember, it's a basaltic system because the partition coefficient also matters here. Because we have to calculate the partition coefficient. So we have to take the individual elemental partition coefficients for system, basalts or granitic or whatever, right? So in a basaltic system, for example, see basaltic and andesitic rocks. So we are taking the respective partition coefficient numbers, right? Rubidium like this. Okay, so that matters. So in a basaltic system, progressive patch melting will result this type of a behavior for highly incompatible elements like rubidium. Okay, so this is what we have to discuss today. But if you have any other questions related to this content, please let me know, because this is a kind of very important model. Batch melting is an important model because it is the most simple type of melting model also, right? So the most simplest type of melting model is batch melting. There are other types of melting models which are a little bit complicated more than this. Right? This is also complicated in one sense, but compared to others, this is less complicated. Okay. No questions?